Hi, and welcome to S for Science. And the energy needed to create a single hydrogen atom is 1.88 gigaelectron volts, which is the same as 10 billion times less than the energy needed to heat 1 gram of air by a degree. It seems pretty little, but with a single gram of matter, you can get 90 terajoules, or what is the same, the energy needed to keep a light bulb on for 285 centuries. But how can matter be created? Albert Einstein's famous equation of energy equals mass times the speed of light squared relates mass to energy. What this formula implies is that mass, in reality, is a type of energy. Mass is energy. But not only that, but from mass, energy can be created and vice versa. If we take two photons that are the particles of the light, and we make them collide, then we will get two particles with mass, an electron and a positron. Collisions with photons with more energy can create a proton and an antiproton, particles that have much more mass than electrons and positrons. But what are positrons and antiprotons? They are antimatter. And what is antimatter? Well, it's nothing more than a form of energy made of particles exactly the same as those that we know, protons, neutrons, electrons, etc., but with opposite charge. Antimatter can obviously create anti-elements in such a way that, theoretically, there is a periodic table of anti-elements, but with unknown properties. In fact, in the laboratory, they have managed to create the first two elements, antihydrogen and antihelium, and there could perfectly well be an anti of anything made of matter. Even an anti-U, made of anti-carbon, anti-hydrogen, etc. Photons are particles that have zero charge, which means they are both particles and antiparticles, in the same way that zero equals negative zero. So with them, you can create both antimatter and matter. And this is one of the problems of creating antimatter and matter. A pair of particles will always be created, a particle and an antiparticle, which, unless they are quickly separated, will collide and form two photons. The thing about matter and antimatter is that, if they come into contact, they release enormous amounts of energy. Both are forms of energy that are very similar to each other and were created just after the Big Bang. But if matter and antimatter are practically the same, and the only thing that differentiates them is their charge, how is it that in the universe there is much more matter than antimatter? It is believed that were generated at the beginning of the universe in the Big Bang equals amounts of matter and antimatter. So how is it possible that they didn't annihilate each other, becoming photons scattered throughout the universe? Baryogenesis is the generic term used to define those hypothetical events that during the beginning of the universe caused an asymmetry between baryons and antibaryons to take place, with baryons being matter particles and antibaryons being antimatter particles. Experimentally, it has been found that for over 10,000 particle-antiparticle pairs, there is one more particle that does not have an antiparticle with which to annihilate and become photons. But that doesn't explain why. In fact, it is currently unknown, although it is believed that it could be because there is a type of interaction that happens more in matter particles than in antimatter particles, and it is believed that this could be the cause of there being more matter than antimatter. But at the end, we're not sure. So now we know that it is possible to create matter, but using photons, so it doesn't count. Can you create photons? Well, yes, it's very easy. You're doing it right now with the screen of your computer or your mobile device. You're creating photons in order to see me. But you're using energy that was created long ago in these stars from matter, so it's not valid. So, can we create photons from nothing? Well, this is something that would break the first law of thermodynamics, which says that energy is not created nor destroyed, it is only transformed. But here is something fascinating. What we know as a vacuum is not really empty. When in a laboratory, a hypothetical perfect vacuum is created, that is, a completely empty zone of space, in reality this space is not that empty. It contains a lot of particles called virtual particles that continuously jump in and out of existence in what is called quantum fluctuations of the vacuum in very short periods of time. But this doesn't happen only in a vacuum, but everywhere. Right now, around you, there are many particles that come out of nowhere to return to it instantly. And it's not just photons or quarks, but particles of matter and antimatter constantly, without ever stopping, wherever you are. But when they annihilate, they create photons, right? Which would actually mean that they are creating energy from nothing and violating the first law of thermodynamics, right? Well, this is why they are virtual. Fortunately, this is fixed with Heisenberg's uncertainty principle, a demonstrated principle that says that the more you know about the variable of a particle, the more uncertainty you will have about another variable. Let me explain. It has been detected that the more you want to know about the position of a particle, that is to say, reducing the indeterminacy of its position, limiting, for example, its space, the more oscillations it will present, making more uncertain what is called momentum, that will influence the direction. It's not that it becomes more difficult to know the direction of a particle, but because of the simple fact that we have reduced the uncertainty of the position of the particle, it will take more directions than if the indeterminacy of its position had not been reduced. Don't worry if you don't understand this. It's quantum physics. It doesn't make sense. It's a very abstract concept, and it's one of the strangest described by physics. But incredibly, this is how our universe works. Applied to virtual particles, the principle says that a particle can have uncertainties in its energy as long as its life, its time, is less than the time required to be able to measure it. Then in this way, the state of a vacuum has an average null energy, but at the same time it is undetermined, thus fulfilling the Heisenberg uncertainty principle, since by giving it very little time, as in the previous example we gave it very few positions, we gave it a lot of uncertainty of energy, as before it had oscillations. And this allows them to be very energetic particles, since they exist for such a short time that they cannot even be measured. In a certain way, they escape from reality. We humans evidently can create many things, like objects and tools, but these things, after all, are made of matter, and therefore of energy, so they don't count. Can we create things that are not energy? We can create perturbations. And these are the waves that, despite not being tangible, are very important in our lives. And there are two types of waves, mechanical waves and electromagnetic waves. They are often confused, but they really have nothing to do. Mechanical waves consist of the propagation of a vibration through a medium transporting energy. An example of them is sound waves, tidal waves, and earthquakes. In the other hand, electromagnetic waves are the result of the interaction of electric and magnetic fields. In this case, there is also energy transported from one place to another, but unlike mechanical waves, electromagnetic waves do not need a medium to propagate. Space-time is sufficient. Some examples of electromagnetic waves are X-rays, visible light, infrared light, radio waves, and microwaves. This is the reason why in this video that you're seeing, where this container with a bell is being turned into a vacuum, every time you hear less the noise that comes from the interior. This is because, as there is less and less air inside it, the sound as a mechanical wave cannot propagate. However, despite having created a vacuum, we continue to see the bell, and this is thanks to the fact that the light is an electromagnetic wave, which allows it to enter and leave the container without any problem, despite the fact that there is no means by which it can propagate. And this is really important because otherwise the light would not propagate throughout outer space, so the sunlight would not reach the Earth. But one moment, didn't I say before that the light was photons? Yes, that's what I said. Light is both a wave and a particle, something that is known as wave-particle duality. And it's something difficult to imagine, but that has been shown to be true. Proof that it is a particle is the fact that it can interact with matter by transferring energy to it. And proof that light is a wave is phenomena such as diffraction. So we come back to the same thing. When we create electromagnetic waves, what we're doing is using energy that already existed to create those waves. But what about mechanical waves? Well, more or less the same. With mechanical waves, what we do is just transport energy, not create energy. So even if we create waves, in reality, we're not creating anything. But people can create something very powerful. Our ideas, our thoughts, our feelings, our emotions, our consciousness, after all, they are nothing more than some very complex chemical reactions that occur in our brain. Something that for us is intangible. But in reality, they emit electromagnetic waves of very low frequency, called brain waves. The frequency of a wave is nothing more than 1 divided by the period, that is, the time between two crests of the wave. That is to say that the larger the frequency of a wave, the more energetic it is and less time will pass between two crests. Waves with a very small frequency, although invisible to our eyes, exist and have wavelengths. The distance between two crests of enormous sizes. They could be defined as electromagnetic tsunamis. On May 20th, 1964, as they worked in what was to be the most powerful radio telescope of that time, Robert Wilson and Arno Penzias detected an interference in the device whose origin was unknown. They tried to clean the antenna and reorient it to be able to find the source of that interference and be able to eliminate it. But they didn't find it. They searched everywhere and the interference was still there. It was of very low frequency. Shortly after, it was discovered that constant low-frequency interference that they had found was nothing more than the cosmic background radiation, or what it's the same, the echo that the Big Bang left. It is a radiation that is found in all places of the universe, and it was formed at the beginning of it, and currently constitutes the most important proof of the Big Bang model. This radiation can be seen on old analog televisions. Part of that noise that appears when it's not tuned to a channel corresponds to the background radiation, correspond to the remains of the moment where our universe was created. Because after all, everything was created in that moment. Everything that was, has been, and will be was created in the dawn of the universe. All the matter and energy that existed, exists, and will exist was created in that moment. The only thing that we can do is create ideas to try to help us understand why we can't create anything. Thank you very much for watching the video, and goodbye.